This is section 3.1, part A, exponential functions. Your I can statements for this section: I can evaluate, analyze, and graph exponential functions, and I can solve problems involving exponential growth and decay. For part A, we're just going to be evaluating, analyzing, and graphing the exponential functions. So a transcendental function is a function that cannot be expressed in terms of algebraic operations, such as an exponential or a logarithmic function. An exponential function is a function of the form f of x is equal to a times b to the x power, where your variable is in the exponent. A and b have to be real numbers that are constants, such that a does not equal 0 and b does not equal 1. In an exponential function, the base b must be a positive number. There are two different types of exponential functions. There's exponential growth. This is an exponential function where the b value is greater than 1. And we have exponential decay when the b value is between 0 and 1. So we need to sketch and analyze the graph of a function. We're going to describe its domain, range, intercepts, asymptotes, and behavior, where the function is increasing and decreasing, and whether the graph is growth or decay. So the first thing we need to do on this is to just make a table of values, so we can plug in x values and solve for y values so we can graph our function. So once we have our table, we pick our x values. We just need to pick values to the left and the right of 0 so we can see what this graph's going to look like. If you put your equation into your y equals, remember you can go to your table and look at your values, or you can do the vars, y vars function y1, substitute in your x value to get your y value. And the y values for our function will be as follows. So once you have the y values, then we can graph these on our graph to see what the function is going to look like. And our graph will look like this. Now we have to find the domain, range, intercepts, asymptotes, limits, where it's increasing, decreasing, and whether it's growth or decay. So if we look at our function, our domain, we have arrows pointing to the left, arrows pointing to the right. There's no place where this stops, so our domain is going to be from negative infinity to positive infinity. For our range of this function, all of our values are greater than y equals 0. It's going to approach it, but it's never going to touch it. So our range is from 0 up to infinity. When we look for our intercepts, our x-intercept, this is approaching the x-axis, but won't ever actually touch it or cross it. So there is no x-intercept. And the y-intercept, where it's crossing the y-axis, when x is 0, our y value is 1, so our y-intercept is 1. An asymptote is a value that the graph approaches but never touches. If you notice, our graph is approaching the x-axis, but it never touches it, so we will have an asymptote at y is equal to 0. When we look for our end behaviors, you're going to look at the left end and the right end. The limit on the left end of our graph, whereas x is approaching negative infinity, our graph continually goes up, so it's going up to positive infinity. On the right side of our function, our graph is getting closer and closer to 0 but never touches it, so the limit on the right side will be 0. On our function, if you look from left to right, you can see that it is decreasing constantly throughout the function. So from negative infinity to positive infinity, this graph is decreasing. And because our b value, we can think of this as 1 times 2/3. Our b value is a fraction. It's between 0 and 1. Our graph is going down to the right, so this is a decay problem. Now if we look at this, you should be able to find at least the shape of the graph without actually having to find all the values. If it's decay, it's going to go down to the right. If it's growth, it's going to go up to the right. Because this is an exponential, our exponent is always going to be our variable. So if I plug in 0, anything to the 0 power is always going to be 1. So as long as this is just a straight exponential function, you will always cross the y-axis at 1 because 0 will always be at 1. So you can always start there and then decide if you're going up to the right or down to the left. So you can do this without making the entire table if you know that information. Now we can use the same techniques that we use to transform algebraic functions when we're dealing with exponentials. So always start with where it's crossing that y-axis at your 0, 1 value, and then you're going to change that value. If you're translating it, you'll move it. If you're reflecting it, you'll flip which direction it's going. So if we look at this example, our normal function is going to be 2 to the x power. Now 2 is a value that is greater than 1, so we know it's going to go up to the right and down to the left. So the original function would cross the y-axis at 0, 1. It would go up to the right and down to the left. And for these, we're just looking for the general shape. They don't have to be completely accurate. But on our function, we have 2 raised to the x plus 1 power. Now, because this is x plus 1, it's attached to just the x. You can think of this as being inside parentheses. When you pull it out, you're going to change the sign. So since it's on the x, it's either going to move it left or right. When we pull it out, this is becoming a negative 1. So that means we're going to move our graph to the left 1 unit. So instead of starting at 0, 1, our graph is going to start at negative 1, 1. It's still going to go up to the right and down to the left. So we do need to find the value for our intercept. If we plug in 0, 2 raised to 0 plus 1 is the same thing as 2 to the first power, and 2 to the first power is just 2. So we do know we're going to cross that y-axis at a value of 2. The only other thing this graph asks us to do is to describe our transformation. This graph is being translated to the left 1 unit. Now on this graph, if we look, we have 2 to the negative x. Again, our original graph is going to start at 0, 1. It's going to go up to the right and down to the left. But this is a negative x. When you have a negative on your x value, it means you're reflecting across the y. So in this case, instead of going up to the right and down to the left, if we flip it across the y-axis, we're still starting in the same place, but we're going to go up to the left and down to the right. So because this is on the x, you reflect it across the y. So our explanation for this transformation is our graph is going to be reflected across the y-axis. In this case, we're taking our function and we are going to multiply it by negative 3. So first, that negative sign is out in front of your function itself, so that means it's on the y. And if it's on the y, it means we're reflecting a graph across the x-axis. We're also multiplying this function by a value of 3. Again, the 3 is in front of the entire function. It's not on just the x itself. So since it's multiplied by the entire function, it's on the y value. Y is vertically. So we are expanding vertically by a factor of 3. Now our original graph, again, is going to cross at 0, 1, go up to the right and down to the left. We're going to reflect this across the x-axis because it is on the y, so it's going to be below the x-axis this time. And we're going to expand this vertically by a factor of 3. So the first thing we need to do is find what our value is going to be if we have the value in front. So 2 to the 0 power is always going to be 1, but 1 times negative 3 Instead of starting at 0, positive 1, if it was just reflected across the x-axis, we'd start at 0, negative 1. But we are multiplying by a factor of 3, so it's going to be at negative 3. And it's expanding vertically, so it's going to go up and down a lot faster. So our graph should look something like this. But the expanding it vertically, make sure you do have it right on the correct y-intercept. We are multiplying that 1 by a negative 3, so it'll be 0 and negative 3 where we're crossing that y-axis. The most common base for an exponential function in real-life applications is not 2 or 10, which is the bases that we use usually in mathematics. But in real life, the most common bases are the natural base. This is an exponential function that has a base of e. So in the previous examples we were just doing, all of our bases were base 2 because we had 2 to the x power, so that means our b value is 2. But the most common one in real life is actually e. E is another number like pi. It's an irrational number that continues on forever. It is approximately 2.718281828, and that pattern will continue. And we reach e if we look at the limit as x approaches infinity. So we're looking at the function on the right. It's the value of 1 plus 1 over x to the x power. So larger and larger values of x is plugged in. It's going to get you closer and closer to the actual e value. If we are to sketch a graph of this, we still have our normal function would be e to the 0 power. E to the 0 power is still going to give us 1. So our original function would start still at 0, 1, go up to the right, and go down to the left. But this time, we are multiplying our exponent, or our variable, by 4. The 4 is just on the x, so this means it is going to be horizontal. And because it's on the horizontal, it's opposite of the vertical, so this is going to compress it horizontally by a factor of 4. So when we graph this, we're still crossing at 0, 1, but it's going to smash it in, so it's not going to take as long to go up. It is going to go up much faster and then go down. On this one, we are going to translate and we are going to reflect. The exponent has our negative sign, so we are going to translate across the y-axis because it is on just the x, so we're reflecting across the y-axis, and then we're going to translate this function. It is plus 3 and it is not attached to the x since it's on the whole function and not just the variable itself. It means we are translating this either left or right. Since it is a plus, not left or right, we're going to translate it up or down because it's on the whole function. Because this is a plus 3, which means we are going to translate it up 3 units. So if here's our original function, the first thing we're going to do is reflect it across the y-axis. So instead, it's going to go up to the left and down to the right. But then we're going to take our function and we're going to translate it up 3 units. So all you have to do is move this point up 1, 2, 3 units. So that means it's actually going to cross at 0, 4. And it's also going to move up our asymptote. Our asymptote was at x is equal to 0. Now our asymptote is going to be, not y, is y at 0, not x is 0. Our asymptote is now going to be y is equal to 3. So it's going to get closer and closer to 3 here and go up to the left. Let's look at one more of these. This time we're multiplying the value out in front of the function. So it's on the entire function, so this means it's vertically. But this value is between 0 and 1, so we are compressing it vertically. by a factor of 1/2. So if we have our original function, instead of crossing at 0 and 1, we're multiplying that factor by 1/2. So 1 times 1/2 gives us 0.5. So we are going to cross at 0.5. And then we're going to go up to the right and down to the left.